Thanks, Yanni, and thanks for organizing this conference. So let's see. Here's a quote from one of my colleagues at Berkeley. I forget who it was who said it, but given its insightful nature, I would say I always guess Dave Patterson when I can't remember which of my colleagues said something interesting. But the thing he said was, this was in the early 80s. In the 80s, he said the most important application of computers has been designing better computers, and I think that's also going to be true for near-term quantum computers, but possibly in a different way than Dave Patterson meant for classical computers. For classical computers, computers really helped us design better computers in the sense of certainly in the sense of CAD, but also creating better compilers, etc. Now, of course, we are in a different world where we already have classical computers that can help us design quantum computers. But looking into these quantum computers is going to be very important in terms of designing better quantum computers, both benchmarking, figuring out what errors look like, as well as coming up with new ways of thinking about algorithms, which is one of the crux of the matter. Okay, but now, as soon as you start thinking about looking inside quantum computers, you realize that there's something very different about quantum computers than classical computers. So, for instance, the time-honored device in analyzing classical computers, a program trace, there's no equivalent of that in quantum computers, because you really cannot probe the state of a quantum computer and still maintain any of its functionality. Okay? Actually, it's even worse than that, because we know that the state of the quantum computer is exponentially hard to describe. Right? That's the whole point of quantum computers. So the state sits inside this exponentially large Hilbert space. But we also know that the laws of quantum mechanics forbid us from actually getting much information about this state. So you can get at most n classical bits of information about this classical state. Okay, and this is this is true even if you add ancilla qubits and under Hollever's theorem. So for all practical purposes, we could think of this our quantum computer as a black box. So once n gets large, we should really think about this quantum computer as a black box. Okay? So that seems to suggest that there's something very fundamental in the axioms of quantum mechanics that keeps us from peering inside the quantum computer. So in some sense, the axioms of quantum mechanics create this veil behind which the quantum world hides. Now, actually, we've known since the very early days of quantum computing that the computational power of quantum computers provides a little way of parting this veil and peering behind it. So, for example, here's something we said back in '93. For example, one might naively argue that it's impossible to experimentally verify the exponentially large size of Hilbert space associated with a discrete quantum system. However, an experiment demonstrating the exponential speedup offered by quantum computation over classical computation would establish that something like the exponentially large Hilbert space must exist. Okay? So it's now a quarter century later, and we actually have this experiment by Google, quantum supremacy experiment, on 52 qubits. So you could sort of say, well, in some sense, it's probing this 2 to the 52 dimensional Hilbert space. Now, of course, there are many caveats in this. As John said yesterday, quantum supremacy is not a point. It's more of a a continuum, and one can ask how well was this Hilbert space explored, and how well was it actually verified, and what's the distinction between the classical and the quantum time, but we'll have better and better experiments over time that will verify quantum supremacy to better and better extents. So all this is in the works. I should also say that there was a lot of complexity and algorithms work that made this experiment possible. There was work by Scott Aronson and his collaborators. There was Brebner, Josa Shepard. There was also work by Adam Bouland and his collaborators. So there's a lot of work that both algorithms and complexity that went into making this possible. But there's one thing that I'd like to say about this experiment, which is that I think, as has been pointed out, it sort of relies on this Goldilocks principle. So why 50 odd qubits? Well, because 50 is large enough so that 2 to the n is an impressive number. But it's small enough so that you can still do simulations on a classical supercomputer. Right? And so if we are going to generalize this notion of a computational probe into Hilbert space and generalize the functionality of it, the first place to start is going beyond this Goldilocks limit. Okay, so let's see what things look like as you go beyond the Goldilocks limit. Well, here's what the picture looks like. So we have we are in the position of this little guy on the left, who has very little computing power and just classical means. And then there's this massive black box with this massive Hilbert space that he's trying to check. Okay, so what does a quantum probe at the Goldilocks limit look like? Well, it looks like that, right? So you make the Hilbert space small enough so that the puny guy doesn't look quite as puny anymore. So is there an alternative to doing this? So here's a way that you can think about it. So what we'd like to do is appeal to the fact that quantum computers are not all powerful. So there are certain tasks that even quantum computers cannot do well. And so the canonical tasks of this kind are what is called post-quantum cryptography. So these are classical crypto systems which you cannot even break if you had a quantum computer. Okay, so what this means is that armed with the secret key, you, as a classical being, can decrypt messages which even a quantum computer cannot. Now, of course, this is a whole big subject. There's this whole effort to transition to post-quantum cryptography, because, as we know, quantum computers are coming sooner or later. Okay, so now once we add post-quantum cryptography to the repertoire, we would hope that that's going to level the playing field between the classical verifier here and this quantum computer. Okay? So there's a little bit to say about leveling this playing field. So what does it mean to level this playing field? Well, there's a wrong way to level the playing field. The wrong way would be to cripple the quantum computer by forcing it to play completely on the classical verifier's turf. Right? That would be really bad, because what's the point of having a quantum computer then? What you want is to achieve this happy medium, where you make the quantum computer play on this turf where the classical player still has an advantage, but you also make sure that the quantum computer can still exercise its unique capabilities. Okay? So that it can exhibit quantum supremacy, it can do all the other interesting things that quantum computers can do. Okay, so how do you do this? So it turns out, well, in my group, we spent a lot of time working on this. And eventually, we figured out one way to do this. So this involved Zvika Brakersky, who's a cryptographer who was visiting Berkeley, and Paul Cristiano, Urmila Mahadev, Thomas Vidic, who are all now former students of mine. So what we realized is that there's a protocol. There's some sort of interaction between this classical verifier and this quantum computer that allows the verifier to force the quantum computer to create a quantum bit. And the quantum bit is in a very special form. It's a superposition of 0 and 1, where there's a phase, and the phase is random. It's plus or minus with equal probability. The bit B is 0 or 1 with equal probability. Now, the quantum computer doesn't know this bit B. It only knows the encryption of B. That doesn't reveal to it what B is. So as far as it's concerned, B is completely random, which means that this state is with equal probability the plus state and equal probability the minus state. And that state is completely indistinguishable from a completely random bit. So from the point of view of the quantum computer, it has a completely random bit. From the point of view of this classical verifier, once it's told the encryption of B, it knows what this quantum bit is. So now the classical verifier cannot really cannot manipulate this quantum bit. It's sitting inside the quantum computer. So the quantum computer has the advantage. It can really manipulate this quantum information. But while manipulating this quantum information, the quantum computer has no idea what this quantum bit is. On the other hand, the classical, this classical verifier has no idea what the quantum bit is and can actually, but can figure out what this quantum bit is. And once you have this, you can do all kinds of things that we'd like to do. So you can do quantum supremacy beyond the Goldilocks limit. Because now the classical verification you have to carry out no longer requires a supercomputer. You can just do it using very little work on a laptop. You can also create certifiable quantum random number generators. What does this mean? It means that you get out a random number, and then you also get a proof that this particular output is random. Okay, so why is that something that's interesting? Well, it's interesting because we need random numbers for various applications, but it's also surprising because in the classical world, there's no way you can do this. It should be clear. In fact, it's even clear to Hilbert that you cannot show that a number is random. Okay, there are also other tasks you can do which are really interesting and surprising. So what you can do is you can use this kind of primitive to do quantum fully homomorphic encryption. So that's a mouthful. What does this mean? So we have a move to place quantum computers on the cloud, right? So there already are many on the cloud. There's going to be many more. And now, if you're going to compute using this quantum computer on the cloud, one thing you might want is to keep your data secret. Right? So how can you do this? How can you have this quantum computer compute for you while keeping the data secret? So you want it to work under the hood. You want to encrypt your data and have the quantum computer work under the hood. There's a way of doing that. There's another thing that comes up. How do you verify that the output of this quantum computer is correct? After all, this quantum computer is exponentially powerful, and so it might be giving us the answer to a very important problem, or it might be just spewing out garbage. How do you tell the difference? Well, okay, there's a protocol to verify the correctness. These were done by Urmila Mahadev, and actually, if you want to read about any of this, there are two very nice Quanta articles that describe it in a very accessible way. Okay, so Giffrey asked me before this talk if there was any science in this talk, and I said yes, there'll be a little bit. I didn't tell him, as a professor, I cannot bear to not give out the secret behind magic tricks. It's a professor is the opposite of a magician. So there's a very simple idea that goes behind all of this, something I can describe to you in basically one slide, and I'm too tempted to do that. So what's the main idea behind all this? So the main idea is we can pick an encryption function E, which has a special property that it's 2 to 1. Okay? Meaning, if the encryption of X is Y, then there's also another message, X prime, whose encryption is the same string Y. Okay? And this encryption scheme has a property that if you know X, there's no way you can find X prime unless you work for an exponential amount of time. And that's true whether you're classical or quantum. So even a quantum computer cannot find X prime if it knows X. Okay? Actually, more than that. If it knows X, it can't find even a tiny bit of information about X prime. OK, so now what do we do? Well, what we do is have the quantum computer pick a Y, and then it's left with an equal superposition of X and X prime. This is something that those of you who worked on quantum algorithms would know as basically the heart of Simon's algorithm. And now, the classical verifier challenges and says, make a measurement either in the standard basis or in the Hadamard basis. So if the quantum computer measures in the standard basis, it's going to, with 50% probability, measure X with 50% X prime. So it sends that to the verifier. If it measures in the Hadamard basis, it gets a tiny amount of joint information about X and X prime. OK, no harm done. It can do both of these. So here's the crux of the matter. The crux is, if a classical computer can answer either challenge, then it can answer both. So why do we know this? Well, it comes from the fact that you can trace a computer program, a classical computer program. So what you can do is, if it was a classical computer that was answering either challenge, it was willing to answer either challenge, you can ask it the challenge, measure in the standard basis, and it gives you back an answer that satisfies you. Then you just roll back the computation. You roll back the trace to where just before you ask the question, and now ask it the opposite question. So you make the Hadamard challenge, and now it's got to answer you still. The point is, with quantum computers, you cannot do this rolling back, but with classical computers, you can. And so since the classical computer must answer both challenges, it's going to give you information about one of X or X prime, and then a little bit of more information. And that's enough to break the crypto system. Okay? So the point here is that this difference between classical and quantum has a lot to do with this fact that there are ways that you can interrogate a quantum system, and there are ways you just cannot interrogate a quantum system. OK, so let me say a little bit about algorithms and challenges. So moving forward, one thing we want to do is, a big challenge is using this ability to probe the interior of a quantum computer to understand noise models for actual quantum computers. So in yesterday's talk, John mentioned that already in these quantum supremacy experiments, you can get some kind of information about the noise model. But we are, at this point, we are far from understanding how to characterize noise inside a quantum computer by doing this kind of it's clear that we have to perform this kind of a probe in order to understand noise models, but how do we do it in a meaningful way, in a probable way? Certified quantum random number generation. This is going to be an immediate sort of application that you can carry out. So Scott has a scheme for this, which actually piggybacks on this Supremacy experiment, the random circuit sampling. That's the one that Google carried out. And so what he showed is that under certain complexity assumptions, small modification of Google's quantum supremacy experiment actually generates certifiable randomness. So, after you're done with your verification on the classical supercomputer, you actually end up with not just quantum supremacy, but some kind of proof that what you got out was a truly random number. The kind of scalable tests that I showed you, there are refinements to those tests, which can decrease the number of rounds of communication, decrease the number of computational steps per round, and increase the number of random bits generated. So with all these, modifications which have been made recently, we are checking to see how far out we are from actually implementing these post-quantum crypto-based random number generators. The advantage there is once we are able to implement these, then the amount of computation we have to do on the classical side is going to be drastically reduced. And also the proof that we have real randomness becomes much stronger. Okay, there's one other feature that we are trying to use in all of this, which is something that was used quite significantly in the Google experiments, which is getting some sort of noise resilience via scrambling properties, right? So one of the things that one can try to use is the fact that if one can guarantee that if there are no errors during the execution of the algorithm, well, then that's great. Then you get the result that you want. But if there are errors during the execution of the algorithm, if you can show that the output looks perfectly random, uniformly random, then actually that's the second best thing to not having errors at all. Because now you can use a large number of experiments to get statistical evidence about what the answer was. So this is, I think, a very important principle to use in near-term quantum computation in designing algorithms. And that's one of the things that we are currently trying to do. Okay, so let me just sum up. So there, even though the axioms of quantum mechanics seem to at first sight rule out any attempt to probe this really complex, exponentially complex nature of Hilbert space, actually computation provides us with a trapdoor through which to do this. And even though the germ of this idea has been around since the very beginnings of quantum computation, we are actually only now beginning to understand how to seriously explore this idea. And together with exploring this idea, I think the thing we are realizing is that if you're going to design design algorithms in this for near-term quantum computers or as they're going to be scaling up, quantum algorithms, of course, we've known for a while that this is really the crux of the problem, right? So that's one of the very big challenges that we face. But the other thing that we are realizing is that to meet this challenge, it's really important to think outside the box, right? There are new ways to think about quantum algorithms, and that's where we really need to go. Okay, thank you. You got the mic.
You mentioned crypto. Is there another application for this? It's a fascinating idea besides crypto, or not yet?
So the question was, is there another? So that I mentioned crypto, which is a way to implement these ideas, but in terms of the perhaps you're asking, is there another way to implement this other than by doing crypto? Is there a different way? So actually, that's a really good question. So at the moment, there's only one way that we know how to carry this out, where you have a single classical entity that's interrogating a quantum computer and wants to sort of get inside its head, right? So what this classical entity is doing is reaching inside the quantum computer and saying, here's a state you must create. It's sort of reaching inside the Hilbert space and forcing it to create certain kinds of states and arrange its Hilbert space in a certain way, right? At the moment, we have this one way of, you could sort of say, we know you have to use cryptography to do this, but we have this one way of sort of enabling this quantum post-quantum cryptography, so that the quantum computer can actively participate in the process while not understanding what's going on, right? But that's what I meant, that we are just beginning to take this direction seriously, beginning to explore this seriously. I believe that there should be many more results in this direction, and possibly many more ways of starting it. Many more starting points on which we can build. Oh, I see. Okay.
Is there like a title or name for this approach?
You're right. We have been quite derelict in doing this because we didn't come up with an acronym for it. So, thank you.
Yes. If you're implementing the Bernstein-Vazirani algorithm, does it require that all the qubits be connected to each other?
Oh, well, you can implement the Bernstein-Vazirani algorithm using a quantum circuit, and your standard quantum circuit model can do it, and you need a certain amount of connectivity, just depending upon you do a Hadamard. Basically, you're using Hadamard, and then you have to look up this oracle. So the question is how costly is it to implement the oracle? But basically, anything you want to do, you can do using 2 qubit gates. So there's no problem with that. Yes.
Shameless plug, I do have a presentation at 1:45 showing some experimental data on the certified random number generator. But I do actually have a question, because a lot of people kind of tell me, it's like, oh, this certified random number generator, it seems pretty useless. Why are you spending so much time on it? What would be kind of your response when people are saying something of this sort?
Well, it depends upon who's saying it. Yes. Okay, so I think that as we move forward, cryptography is, certainly it's used for data encryption, but then over time, in recent years, cryptography is used for much more, right? It's used, there are actually companies that are trying to do homomorphic encryption, encryption, how do you compute under the hood? program obfuscation. So there's this, this higher order functionality in cryptography, and all this depends upon the secret key, right? So there's a lot of cryptography that's compromised because the secret keys are not strong enough. Of course, cryptography is compromised for many other reasons, because people leave their secret keys lying around and so on. So you could say, well, there's lower hanging fruit to be had. But certainly, as you make your cryptographic applications more and more sophisticated, a lot more is riding on, in more complex ways, on the nature of the randomness that goes into creating the secret key. And so, if we can come up with a really efficient, practical, easy to implement way of generating randomness that you can actually trust, that would be, that would take one thing off the table.